Yeah, thank you all for coming. And it's an honor to organize this here and to be back with you. Yeah, so it's actually the first time we're doing the WISE meeting without Luigi. So we had some health issue, nothing very serious, but he was operated on a couple of weeks ago on some I think he was in Reading, for those of you that saw him in Reading. So he's in great shape as usual. So don't worry about him, but we'll have to do without him, so maybe he's online. So hi Luigi if you're there. Actually, I was the one moderating the Zoom, so I don't know what's going on. And so yeah, we've been doing these WAVE meetings for some time, and I joined that. My first WISE meeting was back in 2000, so some time ago in Reykjavik. Some of you were here, not so many. And so there's actually, the great thing about WISE compared to other meetings is that we study waves in the ocean. There's many ways to look at waves. Some people are more applied mathematicians, some are oceanographers, some other people are coastal engineers. A lot of us are actually more into the wave forecasting business and working for the weather services. Météo France is here with us, ICMWF. We don't have anybody from NCEP on site, but they're very much involved in the process. And all these different point of view on the waves actually bring us new things and variety of ways to look at things, and I think that's very useful. And so this year we have a slight remote sensing bias, and I want to thank CNES for funding a lot of this workshop here. So there's actually quite a few colleagues from CNES who came in, so I hope you'll enjoy it. And I think, looking at remote sensing, so you'll figure out what that means. I think in my mind, it's very much related to looking at air sea fluxes, because it's all very much related to shortwave properties. And so hopefully we can make some progress on that. So the program for this week is, yes, could be more Earth interaction today, going through different wave physics processes over the week, breaking wave interactions tomorrow, wave interactions Wednesday, and looking back more carefully at observations on Thursday, and then finally on near shore. So we tend to be the format compared to previous years to try to be more like a summer school. And actually the idea of having a summer school on waves and WISE was an idea of Miguel Honorato, who will be with us soon. So we chatted about that quite a few years ago. And I think it was a great place to do this, so I'm happy we could do it here. And the idea is to not only talk about our research, but also to bring those of us that are far away from specific areas, and also the younger generation of scientists, to understand what's going on. And so this year we're celebrating the 30 years of this book coming out. And so they're all very proud of having produced that thing. So I don't know if who among you have read it or looked at it. I can show a hand. Good. So you probably have figured out that it's not a textbook. It's actually pretty hard to go through, and if you're starting with waves, don't start with that. So you can start with Ian's book, you can start with Leo's book, but this is ugly. And I heard it, I did it the hard way, because the first workshop I went to, I heard about wave science. I mean, I didn't know we could actually work on waves until it was a workshop in '97, Villefranche-sur-Mer, and there was a guy who was very loosely dressed with a rope around his waist, talking about the WAM model quadrant scheme, octant scheme in the Mediterranean. That was Luigi. So I was, wow, you can actually do research on waves. That's funny. And so then I went to the library and picked up a book about waves, and I started with that. It was a very bad choice. So I don't know if we should actually write one book. I'm not sure we're actually wiser than these guys. And among them, most of you would have recognized on the left side as Klaus Hasselmann, or our Nobel Prize winner from a year and a half ago. Pieter Janssen is almost not recognizable. Cameron Common, Susanna Hasselmann, who's very much in the shadow, but I hope that would bring a bit more light on her work. And Mark Nolan, who's passed away, unfortunately, a few years ago. And Luigi couldn't be with us, so these are great people. So one of the questions we'll try to handle this week is how we actually go forward with sharing science information and results, be it good or bad. And when I say bad, sometimes we know we do stuff that doesn't work, and I think it's important to share that fact that some stuff doesn't work. But also we know that some of our papers that get published have some errors, or maybe should be all the way retracted. And so how we actually share that information about stuff which is in the literature, which actually, has some issues. So should do like notes to the community like they do on Twitter or whatever, I don't know. But anyway, so science made by people and for people, and it's not just a PDF sitting on a hard drive waiting to be parsed by an AI. And I think we have to appreciate that fact that it's all about people interaction, and I think it's great to have you here. So we have the talks, we have the posters. By the way, for those of you that may complain that they are on the back side of the poster, we'll flip the posters order at the middle of the week. And then there's a lot of time during this week to interact and chat. So hang around, grab people. You can work on these chairs. You can just go and watch the waves. It's going to be a nice show, hopefully tomorrow and the day after, with nice waves in the ocean. And the idea is to have plenty of time to discuss and go forward. And we'll have a session at the end to go back and see what we want to, how we want to change things about how the waves is run. Before I forget, there's one thing, maybe I have to give the floor to Ton for a few minutes about the WISE Zoominars. So we have these workshops we do like once a year, and then we started trying to do these Zoominars online. By the way, they're available on YouTube, so you can go to that link and find them. And maybe Ton wants to say a few things about what's going to happen with Zoominars.
Do that at 4 o'clock, or do you want to do that?
Whatever.
Slides, so maybe
Later? Or we'll do that later, but yeah. Yeah. Good. So that's pretty much it about the organizational stuff, and then I can move on to the science, and then I'll cut off wherever in. So, yeah. Sure.
Zoominars, Australian time, always early morning, right? And that's China as well, Japan, Korea, right? So we're out of that, right?
Yeah.
So maybe it's worth rotating, right? So
yeah.
Sometimes Americans are missing, sometimes us, right?
Yeah.
I understand.
No, that's a fair point, and we'll discuss that. Yes, thank you. So I'll try to introduce you to waves. So it's going to be pretty boring and stuff that everybody knows. Hopefully I'll try to put in a few newer things in there. And the waves, wave spectra, and source terms. So this is one way to think about waves. Aha, that's lovely. I love this. Which means that I have to change the mode of that thing. And then it's a question of sharing and having duplicate screen. Can anybody know how to handle that on Windows? The fact that you may have... Yeah, but if I do this like this, it's not going to be very nice. So there's several options. I guess I could have to duplicate the screen. So if somebody can do that on Windows, but I'm not a Windows guy. No.
Stop sharing. Stop sharing. Share again the entire screen.
So this. All right. It's okay. I guess that's the best solution. Or we'll work towards perfection for the next talks. I guess perfection is not part of this world. All right. So what you have on this diagram is actually 4 maps of the same day, which is June 6, 2023, last year. And I picked that day for some reason, which is explicit on the poster. Maybe I'll go back to that. So we got the wave heights, which goes up to 17 meters in that big storm. And then it gets other funny parameters, which I added in WaveWatch recently. One is the spectral peakness, which actually tells you how groupy the waves are. And actually that's an interesting parameter for measuring the variability of wave height measurements in altimeter. This is the skewness of zero slope points. So if you take the joint PDF of slopes and elevations and look at the skewness of that PDF estimated at zero slope, that you get this kind of map. And this is big thanks to Peter Janssen for the code for computing that, which was in WAM, but you can put that in WaveWatch. So you can compute skewness from the wave spectrum. And this is a similar kind of skewness, but it's a joint skewness between elevation and slope variance. And that's supposed to be the assisted bias for altimeters. We can predict from models. For some reason, space agencies actually don't use that yet. I don't know why, and probably it's not good enough for their purposes, but I think that's something that should be investigated, and I'll mention that a bit later on. So there's more than just wave heights to what we can do. So waves are, can be described by many effects. So their surface elevation, velocities in the air and water, the pressure, the displacement of the particles, the acceleration, and surface slopes. And very often we start with the Eulerian surface elevation, and that we assume to be single valued. So at any point in x and y, there's only one value of zeta, so you don't have the wave turning over. So it's a nice poster with turning over waves, but I'm not dealing with that here. And they can do it Eulerian or Lagrangian from initial positions. And then very often we start with, assuming that flow is irrotational. So we'll know from our Norwegian colleagues that this is actually not very good for everything. So it is a small vorticity, but we'll just forget about it for now. Irrotationality is very nice because you go from a 4D problem of xz, xyz, and time to only 3D. 2D in space and time, because then you have a Laplace equation that actually maps the vertical on the horizontal, even for nonlinear waves. And so you have this full picture for linear waves of the flow field, the pressure field, and the particles moving. And just to remind you, there's also velocities in the air. Yes, there's a big jump here, and I should know how to do this stuff here. So there's a big jump in velocity from here to there, and this is just because I'm using airy theory. Dor has a nice continuous version of that, and so forth. All right, so that's very simple things. So the first thing we looked at very often is the amplitude of the waves, and for random waves, that's going to be defined by the significant wave height. And so we take that to be 4 times the standard deviation of the surface elevation. So my variance of the surface elevation would be E, and so 4 times square root of E would be the wave height. And so that's just the way you compute that. So you take the variable you're interested in minus the average and take the square of that. And for this record here in time, that will give you a wave height of 1.8 meters. Yes, okay, so I have to do this magic thing. I don't know how to do this with here and there. So you're going to save me again. Sorry. This? Thank you, Evan. All right. It's getting better a bit all the time. So here I use this average over 400 seconds, but why that scale? I mean, if you actually average over a very long time, actually we have the tide in there, because this small piece of time series is part of the tidal cycle, so you certainly don't want to have the tide into your wave height, right? So we actually have to be a bit more careful in defining how we do things, so probably we have to define some scales, all right? And very often we do that through a spectrum. And so when you do a spectrum of that, you get this kind of spectrum. And so one of the questions is, okay, should I include the infragravity waves, so this very low frequency part of the spectrum, into the wave height? So you could do yes or no, and that's just some convention. But all these small details are actually relevant in the end. So we'll hear more about infrared waves in the end with Yaron Toledo on Friday. So okay, we do 4 times the variance, the square root of the variance. And so in practice, we actually chop off at some minimum frequency or maximum frequency, or if we do it in space, at some spatial scales. But then there are some issues with the variability of this estimate. If you do that over a shorter time scale, you're going to have a wave group and no wave group and a wave group. So should we include the variability of wave height inside of the wave groups inside the wave height? I would say no, but that's something to be debated. So just to point out that simple things are actually not that simple. I'm getting some feedback here. All right, so from waves, then the scales, as we look at spectra. So these are some examples of wave spectra from a wave model run, and so at different time steps. So you have, this extends to infragravity waves, and then the usual Wincy and swell. And the nice thing you can do is to, when you start looking at spectra and you want to predict things, you going to say, okay, well, waves are almost linear, and so maybe we can just go along with the linear wave dispersion, and that will actually map our 2D plus time into just 2D in total, because there's connection between the space and time scales through the dispersion relation. So that actually makes our problem much more simple, in that we're only to deal with a 2D space for describing the sea state. And of course, very often we only have 1D spectra because from time series. And here I just want to highlight what I think is actually the most beautiful spectra I've ever seen, which is coming from this pressure recording at the bottom of the Pacific Ocean in 5,000 meter depths. And this is showing the pressure from 10 to the minus 2, so 100 seconds, all the way to hundredths of a second. And that's the pressure at the bottom of the ocean. You can see beautifully the infrared waves, the Swiss and the swell, and all the wind sea all the way to capillary range. And that's something we still have to explain in detail. All right, so linear wave theory. So the nice thing we do is, okay, we're going to superpose a bunch of cosines and sines. You can do that Eulerian or Lagrangian. Some complementarity there. And the nice thing is that for each component, you have a connection between the surface elevation and the full velocity and pressure field in the water and the air. And so that nice thing is you can use just a wave spectrum to estimate the spectrum of any other quantity with the pressure, velocity, or vice versa. If you have a measurement of acceleration or pressure, you can go back and invert that to get the surface elevation spectrum. That's all nice, but of course waves are not exactly linear. Otherwise, a lot of people here will be very bored, so we'll have much more non-linear stuff on Wednesday. But basically, we have the advection equations in the Eulerian equations, or the mass conservation for the Lagrangian equations that introduce some nonlinearity. And the good thing with waves is that these nonlinearities are small, and so you can actually expand the fields into linear parts plus corrections. So for the surface elevation, do like zeta. The surface elevation will be the linear part zeta 1, which is that thing here, plus some correction at second order, third order, and so forth. So you can do that with Eulerian solutions, and you can follow, for example, derivation of Hasselmann for the wave interactions. You can also do that for Lagrangian coordinates. That was done by Pearson, as a nice paper by Frédéric Nouguier, also in GFM 2009, doing the second order Lagrangian velocity field, elevation field, which is a nice way to also look at remote sensing problems. But do we actually need to worry about zeta 2 and P2 and so forth? And so for some applications, and actually I'm going to say for most applications, yes, you have to worry about that. And just to go back on this spectrum, this is actually a second order pressure field due to wave-wave interactions. So all of this is actually second order. And when you look at the bottom of the ocean, the second order is actually much larger than the first order. So it's not because it's second order that it's small. In many places, actually the second order is larger than the first order. So you have to worry a bit about that at the bottom of the ocean. But what about the surface where we are? And so I'm going to get you through a short trip to the Black Sea and the Katsiveli platform, where many of our ex-Soviet colleagues used to do some nice work. And so we went there with Alvise Benetazzo in the early, 10, 15 years ago now. Boy, time flies. And so you basically have a set of cameras, and you look at the surface. You have the left and right view of the surface at one time step and the next time step, and you make a video of that so stuff moves. And so you can reconstruct surface elevation, so that would be the surface elevation field at one time step, and the next time the waves are moving that direction. And so all the details of the method are described in Benetazzo, I think 2011 paper. And that specific work is from a paper by Leclerc et al. I'm going to show, and also part of the data set that was put together by Pedro Guimaraes. So first thing we did is, okay, we're going to look at the 1D spectrum, so surface elevation. We'll compare the video data at one point with the wave gauge. And you can see we have some wind sea peak here at about 3 seconds, so it's pretty short waves, short fetch conditions. And we can actually go all the way to maybe 1.4 hertz with the video data in terms of that quantity. And then you can start looking at different things, because you have actually not just 1D measurement, but it's actually a 3D measurement. So you have a cube of data in X, Y, and time, and you can make a slices on that. So the bottom plot here is a slice in the Fourier spectrum. So you transform X, Y, and T into frequency, Kx and Ky, the two wave numbers. And if you slice that spectra, you get this kind of image. And where you have the dispersion relation, but of course you have nonlinear contributions, so you have second order harmonics on this thing. And if you slice on the other direction, make horizontal slices, that actually shows us even stronger. So this is closer to the peak. So the peak is actually at 0.3, so it's at 2 times the peak frequency. This is at 3 times the peak frequency, and we're going all the way to 4, and maybe 4.5 times the peak frequency. And you can see that there's this blob of energy here at high frequency is, yeah, this blob of energy here at high frequency is really the second order term which is coming from that. And so you can actually check the theory, and if you take the frequency spectrum at 4 times the peak frequency, so that's be here 1.2 hertz, I believe. So the linear part is only the blue curve, the measurement is a pink one. If you take the second order term squared, which is part of the second order spectrum, you go over the measurement, but if you take into account the correlation between third order and first order, which is that term here, which is the second piece of the second order spectrum, then that brings you actually pretty close to the measurements. That would be the dashed red line. So basically the theory for the second order spectrum can be verified with serial video data, and actually works pretty well. And the code for computing that, again, is thanks to P. Janssen, and that's actually using the canonical transform from Krasicki. And the code for that is in WaveWatch for those that want to use it. You can just post-process your spectra with that stuff. And if you do an MEM on this spectrum, the pink one, you get this double peaks thing, which is actually just MEM making up stuff. Of course, you can also look at the wave number spectrum. And for the wave number spectrum, the linear spectrum and the full spectrum actually are much closer. And that is because the harmonics are in a way that they only show up, well, they mostly show up in frequency and not so much in wave numbers. So remote sensing for wave number spectra is actually very good for separating the linear and nonlinear part, or actually not having so much issue with nonlinear terms. So the good news is we can actually compute the second order spectrum, E4. Not very many people have done that so far. And before you go to this second order spectrum, you can also compute other parameters which are related to the second order correction, zeta 2. And these are including in the moments of the joint elevation slope PDF, which I was mentioning at the beginning. And so these maps are computing using that stuff. And it's based on the full theory is based on a paper by Shrokos, which actually computed how you can get the second order correction from the linear spectrum. So it's not because you only have a spectrum of supposedly linear waves that you cannot access the nonlinear terms. And that's something which I think we should use a bit more. Okay, so we have spectra, and so now we want to predict, we cannot have video cameras everywhere all the time. And so if we want to move somewhere in the past or in the future to know what the waves were and what they will be, we need some predictive model. And so for that, people have worked with spectral wave models, and that first was done for swell forecasting, actually in the coast of Morocco. The swell forecasting service of the French Navy was established in Casablanca in 1922, more than 100 years ago. They were using observations in the Azores to predict waves arriving in Morocco. And they actually had a first analysis of swell dissipation. There was a paper in 1937, which I haven't found yet. So if some of you have access to the Annales Chériféennes, so there's some special journal from Morocco that has that paper. And it's actually cited in the report H0601 from Sverdrup and Monk, because they actually used that swell dissipation estimate in their wave forecasting paper from 1947. Anyway, so swell is actually a nice thing because it disperses, so different wave periods travel at different times. So it's kind of logical to do a spectral wave model. And that was taken to also wind speed forecasting, thanks to Klaus Hasselmann and his work, because they found out that nonlinear interactions were actually very important. So you can write the evolution of the wave spectrum in time as a sum of different source functions. So for each frequency and direction, you have some source of energy from the wind, some transfer of energy from one component to another, which is this SNL, and then some dissipation, some energy is lost from the wave field, and you can account for that. Mostly due to wave breaking. And so the very good news in terms of what I was saying about the E4, this nonlinear spectrum, you can actually fold some of these nonlinear terms instead of the linear part using the Krasicki transform, and you don't have to worry about the nonlinear evolution due to this bound waves, essentially. And I'm not the right guy to explain that to you, so maybe Miguel or other people will do a better job of me than that. The bad news is that nobody has really worked out what the impact of E4 was for the other terms, the input and dissipation. So we still have to think about these terms and what they do to wave breaking and maybe wind input. Okay, so if you look at what it does when you integrate over directions, that would be an example of energy balance. So the different source terms are the input in blue, the Nordian term in green, and the dissipation in this funny brown color. The sum of the three is a red line, and to scale it, compare it to the wave spectrum in black. So in this case here, I have multiplied the source term by 1,000 seconds, which basically tells you that the time rate of evolution of the spectrum is about 1,000 seconds, and that's if you start from a rest and you blow the wind on the numerical model with a 50 meter per second, and after 3 hours you get this kind of situation. So initially the waves evolve pretty fast, and as you march forward, the source term will lead to an evolution of the spectrum, and so the peak of the spectrum in black here will shift from 0.25 hertz, so 4 seconds, down to something which is maybe 0.08 hertz, so 12-second period. And when you get to that stage, you can see that the source term I had to multiply it by 10 to the power 5 seconds. So basically, the evolution time scale at that stage is about 1 day. So went from something that evolves very fast, a young wind sea, to a very mature wind sea that evolves much slower. And then we get the balance of the source term at high frequencies, with the input mostly balanced by the dissipation and the nonlinear doing some bit of transfer there. Some people would argue, okay, how do you know the magnitude of these source terms? You only have observations of the spectrum, and that's a very fair point. And until, I don't know, 15 years ago, NCEP was actually running an operational model where the source terms were all 2 or 3 times lower than what we have today in WAM or WaveWatch. And you could get away with a factor 2 or 3 error in the source term. We're not sure it's an error because we don't really measure them. But there are some consistency checks you can do, and so there's still a lot of questions into what should be the actual magnitude of these source terms. And so there's this very nice work that was put together by Klaus Singer back in '91. Before WAM, people actually would fudge with the spectra and say, well, that should be the shape of the spectrum. And basically we put all the fudge, or call it art, into the source terms. So there's still a lot of fudging there, but at least we're trying to have a physical basis for how the wave spectrum evolves. And I just want to highlight here, so if that is actually art, well, the true masterpiece is that art is something which is still with us today, which is this discrete interaction approximation. So it's a paper by Suzanne Hasselmann et al. From 1985. So I wasn't there at that time, so I don't know how much, who did what in the co-authors, but she's the first author, so I guess she came up with the idea, or maybe Ian will tell us later the story behind how the DIA happened, but it's actually a pretty amazing thing that it's very crude parameterization, and people are still using it a lot, and I want to show you what it gives. So basically, for wave interactions, so you have some resonances. So I was doing this expansion from zeta 1, zeta 2, and so forth. So at some point when you solve for the third order elevation part, you find that there's some resonance, and then you get some amplitude which is not bounded, and you can compute the rate of change of that amplitude based on the interactions with some resonance that occur, and you have what we call quadruplets. So you have a combination of 4 wave numbers that come together, such that K1 and K2 equals K3 plus K4, and the corresponding frequencies have the same rule that F1 plus F2 is F3 plus F4. And because of this constraint, that actually gives you only some specific wave numbers can actually interact. And so out of the 6 possible dimensions of interactions, you reduce that to 3. And that would be a typical geometry of K1 plus K2, which here actually happen to be equal. K1 equals K2, and that will be equal to K3 plus K4. And that particular geometry was chosen for parameterizing as a DIA, and it is just one out of many. And when people say that they actually have only these 2 interaction configurations, so meaning that you have these 2 triangles symmetric, but you actually have to think that each component can be any part of this triangle. So in the code of the DIA, if you look it up, you'll find that there's actually, for each spell component, it will actually interact and exchange energy with within 6 quadruplets, which means it's actually exchanging energy with 12 of the components. So if you draw a diagram, basically our component at F and theta will interact with all of these components in blue. So some of them are at higher frequencies, some of them at lower frequencies. You get a direct cascade of energy towards higher frequency with energy being transferred to higher frequencies, and an inverse cascade to lower frequency with energy being transferred to the other shorter wave numbers. All right? That's the DIA in a nutshell. And then you can go through the code and have some fun. And if somebody wants to actually have a Python version of that DIA code, which seems to be working. And then there's interpolation spectra, so we actually have 48 components interacting with something. But it may sound like a lot of interactions, but it still is a small fraction of the total possible interactions. And so we've been stuck with either doing some very exact heavily computation for the non-interactions, or this very crude DIA thing for a long time, and we know it's actually not very good. There was a nice paper by Banner and Young showing that the DIA behaves like a spurious dissipation for the high frequency part. And but then Igor Lavrenov came up with a faster method to compute that, and Michel Benoit took that up and had a very nice code for computing this. And I'm going to show a few results of that, but Michel will show, I guess, more detail on Wednesday. So this actually map comes out as a GQM calculation on global scale. It's showing the wave heights of waves longer than 18 seconds for this 6th of June storm I was looking at. The red line on top of it are the SWAT ground tracks, and the squiggles here are where I have some spotter buoy data. So I can check on the DIA run or the GQM run and compare that to the buoys, and you'll see that the spatial distribution with a DIA is actually pretty broader here than it is with a GQM, with the exact calculations. And that tells us something about how broad things are happening. If you actually look at the buoy data, it would seem that here maybe the DA is better. In other places it's not, and so it's still not clear who's the winner. And if you look at time series of different buoys, so here you would see the GQM run will actually be right on top until almost the peak of the storm, and the DA will be too high, but then it's actually better for the rest of the storm. And just to let you know that we've been playing with the DIA for such a long time that now we have to unlearn and do a lot of stuff with the more exact calculations, and that can be done now in real time thanks to Michel Benoit version of the code. So I don't know how much more time I have. All right, and that would be with questions or? Okay, so I'm gonna have to wrap that up. So you have the slide for the rest of stuff. I had a lot of stuff on the dissipation and Romero source term, but I guess Lionel will take it up from wherever that is. And so I talked about the nonlinear terms. There's a dissipation term. We can say a lot of things. So there's many dissipative processes that are happening. Wave breaking is on top, but it's only one of them. We have air-sea friction. We have the stretching of turbulence by the Stokes shear. We have the modulation of torsion by the long wave. We have many other things, and we have to keep. And if you actually work in an Earth system, which I think we should try to do, then it's not just enough to take energy out of the wave field. You have to track where the energy goes, because that may be doing something different in different places of the Earth system. And so instead of writing the wave energy, the energy balance equation here. I think it's better to break it up into, okay, we have some energy from the atmosphere, some energy distributed in the wave field, some energy going to, something happened weird here. So there's some current effect here, some ice, maybe the bottom, and the ocean part, yeah, there's an OSO missing. So the ocean part, you can actually break into current and turbulence. And the important thing is, if you integrate the source terms as such, that will give you a net flux of energy with the units of watt per meter squared. If you integrate times the wave number divided by sigma in the integral, that will give you a momentum flux with units of pascals. And so these fluxes are actually relevant for the other parts of the Earth system, and we have now to think more, I think, the source terms in that way. So I'm going to skip a lot of that. Just one mention is, at some point, maybe we wanted to measure stuff directly from space, of solving wave action and wave models. Just to highlight you the fact that we're getting many more different remote sensing options these days. We will soon have a P-band SAR flying in space. We've had L-band scatometer for some time. We used to have C-band scatometers. Ka-band are coming soon. W-band is actually what being proposed for ESA as part of Wyvern, and we're getting some nice echoes from the ocean surface. All these things are sensing the surface with different wavelengths, and so actually measuring the amplitude of very different wavelengths. And if you do optical measurements, then you're actually measuring the PDF of the slopes in one particular direction. So remote sensing is very rich, but it doesn't always give you directly the quantity you want. So it's something to be mindful of. All right, so then I'll just jump to my conclusion then. This is all Romero stuff. Yep, here you go. So yes, we can think about waves being modeled by a spectrum, and that can include nonlinear effects. For the spectral evolution, we do some assumption about the dispersion of the waves and physical processes and how we parameterize them as source terms. We have to be careful about source term integrals that gives us fluxes, which means we have to be serious about the source terms and the magnitude and their shape. And I want to point out that parameterization can have very strange side effects. You can call them unphysical features or physical bugs, but they're problems with parameterization. And learning from these problems or from successes of parameterization, I think is very important. So we have to take parameterization seriously and look at what they do and all the different terms. So there used to be a very bad problem with the Wincy and swell interacting, the WAM parameterization with dissipation. There's a DIA spirit dissipation that we pointed out. There's a funny small effect with Romero dissipation, maybe we'll talk about it. And my parameterization for swell dissipation initially had some very bad side effects. And so all these things are teaching us something about the true physics when we compare this parameterization to the real world. I think we have to look at that from a scientific point of view, not just an engineering point of view. All right, and I think that's all I have, pretty much.